Hi everyone, welcome back to Mind Maths with Amina. Today I'm going to solve question number 2 given in the final exam for the course topics in mathematical methods. Okay, the question says, consider the following system of difference equations. Reformulate the model in matrix form. So let's first convert this into matrix form, which is easy enough. We'll have the coefficient of xt minus 1 is a 1, yt minus 1 is a 2. We have a 3 and a 2 here. Okay. Then we have a xt minus 1, yt minus 1. And we have a column vector 5 and 3. Okay. Okay. The question wants us to solve the model for x and y using the eigenvalue and eigenvector approach. So that means you're not supposed to find like a general solution and by adding the homogeneous solution to the particular solution. You're not required to do that in the question. You need to solve this using eigenvalues and eigenvectors, which is basically using diagonalization. Okay, let's call this column Z. Let's call this 2 by 2 matrix A. This is same but Z but lagged one period behind, plus some column vector G. Okay, remember A minus lambda into identity into V, when we put it equals to a 0, lambda is basically the eigenvalue, is known as an eigenvalue, which is associated with the eigenvector V, and we call this the associated eigenvector. Okay, so and the matrix P has in its columns the eigenvectors. So the column entries are going to be the eigenvectors, and the matrix D has the eigenvalues in its diagonal entries. So if you're familiar with diagonalization, we know that if a matrix A is diagonalizable, then P inverse of AP gives us the diagonal matrix D. Okay, so we want to do a change in variable by assuming that ZT is P multiplied by MT, where MT could be any is another column vector. You can say MT and T. Okay. So our system was this. Okay, so I'm just going to substitute this equation into this one. Okay, so on the left hand side I'm going to get a P MT. On the right hand side I'm going to get a P MT minus 1. Okay, the reason being, if I lag this one period behind, the matrix P is just constant, right? So it doesn't get lagged. However, M does get lagged, so both get lagged. Okay, plus a G. Let's take P inverse and multiply it on both sides. P inverse of G. And here we are going to get diagonal matrix D, MT minus 1, and P inverse of G. You can think of this giving us the particular solution and this giving us the homogeneous solution. Okay, so once we find the value of MT, we're just going to put it in this equation. Let's label it actually so there's less confusion. I'll call this equation 1, or maybe I'll call this equation, the first one, equation 1. Let's call this equation 2. And in the first step, what I did was I'll write the instructions. I put 2 and its lag in equation 1. Okay, and once you find empty, put it in 2 to find the final solution. So that's really just it. All of the students in this batch were unable to understand this procedure. Even the most brilliant student in this batch couldn't understand this procedure. I don't know particularly why, because it's quite simple. So I think maybe it's just practice will make you perfect. Maybe that's it. Okay, so let's start. Before I actually start the actual solution, one thing everybody should know is that if, for instance, I have a system yt is equals to ayt minus 1 plus a b, then once you find the particular solution and the homogeneous solution and you add it up, the solution overall, the final solution, is basically the initial condition of y, okay, minus the particular solution, which in this case is going to be b1 minus a, and then you have the root lambda power t, and in this case the root is going to be a, okay, plus the particular solution once again. So this is something you should just know by heart in any case. How I found this, I've already recorded a lecture about this, how to find the general solution by adding the homogeneous solution and the particular solution. So just if you've forgotten this, you can just refer to that lecture. Okay, so continuing. First of all, in order to do all of this, I need the matrix P, right? And I need the matrix D. I already have matrix A. Okay, so let's find these. So we need to find matrix P and D. Remember, the matrix D is obtained as a result of solving the characteristic equation, which we get when we are finding the homogeneous solution, which in this case we don't really need to state it because the question doesn't ask us to substitute any trial solution. Okay, so finding out the okay we need the determinant of the characteristic equation. Actually let me write it down like this. Okay, the value of v is not equals to a 0, right? Because it is an eigen vector. Therefore the determinant has to be equals to a 0. Otherwise, if it was not equals to a 0, then the inverse of this matrix would exist and it would just give you a trivial solution, right? We don't want the trivial solution. So let's find out a minus lambda I determinant and put it equals to a 0. A was a 1, 2, 3, 2. So minus lambda, idhar kuch nahi, minus lambda determinant is equals to a 0. Okay, we have a 1 minus lambda into 2 minus lambda minus a 6 is equals to 0, which becomes a 2 minus 3 lambda plus lambda square minus 6 is equals to a 0. Lambda square minus 3 lambda minus 4 actually. Minus 4 is equals to a 0. Then we have of minus 4 plus 1 minus 4. Okay, that's fine. Then we can take lambda is common. We have lambda minus 4 plus 1. Lambda minus 4 is equals to a 0. Lambda plus 1. Lambda minus 4 is equals to a 0. Okay, so the one root is a minus 1 and the second root is a 4. As you can see, because these are difference equations, right? So the only way we can have a steady state which is stable is when the absolute value of the root is between 1 and 0. This is when we have a stable steady state. However, as you can see, the absolute value of the first root is a 1 and the absolute value of the second root is a 4. That means whatever steady state that we have is actually unstable. So what this means is, I'm just making a rough sketch. I'm pretty sure these lines aren't. Suppose this was the YT or this was XT. So this steady state right here, if by some coincidence the economy stays here, then it's going to stay here. Okay, so this is the steady state. But if there's any kind of shock to the economy, then the economy is not going to converge back to the steady state because it's unstable. So what we can imagine is that whatever trajectories are being made, they basically take us away from the steady state. We don't have a steady route in both directions because we don't even have a saddle steady state. Okay, so there is a steady state, but it's unstable. Some students get confused when they see instability. They automatically think that there is no steady state in the economy. The steady state, I'll repeat, still exists, but the only problem is that it's unstable, which means that if the economy is subjected to any kind of shock, the economy will struggle to or either basically never come back to the steady state. Okay, so we have two eigenvector values now. So the matrix D becomes -1, 0, 0, 4. Okay, let's find the eigenvalues. So the first eigenvector will be the solution to this system. Okay, we can let's just first write the system. It was 1 minus lambda, 2, 3, 2 minus lambda into, let's just say this is x, this is y, and this is a 0 into 0. Okay, when a lambda 1 is equals to a -1, so we have the augmented matrix as follows. This is going to become a 2 and this is going to become a 3, and we need the augmented matrix. Okay, we can multiply the first row by half, and we can multiply the second row by 1 by 3, and then when we do this, we'll get ones everywhere. Now we can do row 2 minus row 1, and as a consequence we'll have infinite many solutions because now we have two unknowns while we have one equation. Remember, x is in the leading one position, whereas y is a free variable. A lot of the students in this batch didn't know how to maneuver this. X plus y is equals to a 0, where y is free and you can substitute it as a t. So x is equals to a minus y. So if if you take 1, y is equals to a -1, then you'll get x is equals to 1, or it could be the other way around. Anyhow, so y is a -1 and x is a 1. So this is our first eigen. And also don't worry, like if you took y is equals to 1 and as a consequence you would have gotten a -1, it's the same thing. You're not gonna get penalized for that. Okay, let's find out the next eigenvector. It's going to be a minus lambda 2i into v2 is equals to a 0. Since lambda 2 was, I believe, a 4. Yeah, So we're going to solve this system again to find the eigenvector. So a 1 minus a 4 is going to be a minus 3. We're going to get a minus 2 here. Let's make the augmented matrix. Okay. So this is just basically a row 2 plus a row 1. And again, we have zeros in the last row, which shows us that we have infinitely many solutions. X is in the leading one position. Therefore, y is a free variable. And we have a minus 3x plus 2y is equals to a 0. Therefore, x is equals to minus 2 over 3 into y. If we take y is equals to a 3, then we can avoid a fraction, right? So if we take a 3, we'll get a minus 2. So we have... did I write it properly? I'm feeling a bit... wait. This was... what was... we had a 1, 2, 3. Okay. Yeah, this is fine. So we have right here... Oh, actually, wouldn't this... Oh, yeah, it's a positive. Okay. So v2 is going to be, if y is a 3, then x is going to be a 2. Okay. So moving on, we had d is equals to a minus 1, 0, 0, 4, and the corresponding P matrix is a minus 1, 1, and 2, and 3. Okay. We also need the inverse of matrix P, and since this is a 2 by 2 matrix, that's very easy. We have a minus 3, minus 2, and we'll get a 3 here, minus 1 here, minus 1, minus 2. Okay, so therefore we have a minus 1 over a 5 into a 3, minus 2, minus 1, minus 1. It's conventionally like preferred to remove the negative sign, so let's just put a 1 by 5 here and put a minus 3 here, 2, 1, 1. Yeah, that looks better. Okay, so now that we've found out all of this, let's see what our final solution should be. It should be this. Okay, so MT should be equals to the diagonal matrix, which is a minus 1, 0, 0, 4, into the column vector lagged 1 period behind MT minus 1, small nt minus 1, plus this P inverse, okay, into G, and G I believe had a 5 and a 3. I'm forgetting, let me just scroll up and verify this. Yeah, a 5 and a 3. Okay. So then we have a minus mt minus 1. We have a 4 nt minus 1. And on this side, we're going to have a 5 3s are 15, minus 15 plus a 6, and a 5 plus a 3. Okay. So that basically becomes negative 9, right? And a positive 8. Okay. So basically, MT is a minus MT minus 1 minus a 9 by 5. And we have nt is equals to 4 nt minus 1 plus an 8 over 5. And initially I showed everyone how to find the solution to such a system. We've already covered a video over it. So this is how you find the final solution. I'm just going to write it down. You find the homogeneous and the particular solution and you add it up. Okay, so in this case, MT is, let me just put an arrow first. MT is going to be m naught, which is the initial value of m when time is equals to 0, minus the particular solution, which in this case is minus 1, 9/5, and a 1 minus a minus 1. Okay, then we have a minus 1 power t, and then we add the particular solution, minus 1. Okay, let me move this down so we can write the solution of MT. MT is equals to m naught, and we have a positive sign here, and over divide by 2, the 5 2s are 10. Okay, and this, then we have a minus 1 power t, then again we have, actually now this is just going to be a minus of 9/10. Okay, so let's do the same for NT. The general solution is going to be initial solution minus the particular, okay, which is a 1 minus 4. Okay, the value of lambda is a 4 power t plus the particular solution, which is a 1 minus 4. Okay, so the final general solution is going to be NT. It's a 3, right? So minus 3 becomes a positive. Okay, 8/5 3s are 15. Then we have a 4 power t, and again 5 3s are 15. So we have the value of MT right here and NT right here. Okay, the final step, the final solution. Remember, we wrote that when we were doing the change of variable, equation 2, we wrote ZT, which we wanted to find, is P into MT, right? So that means XT and YT is equals to the matrix P, which was a minus 1 2 1 3, and MT, which we've actually found right now, MT NT. Okay, so therefore the final answer for XT is going to be minus MT plus 2 NT, and we're just going to rewrite this. Okay, when we've multiplied by a minus 1, we get a plus a 9/10 here. Okay, let me move it more to the left so it fits. Then we have a plus 2 into the solution. Okay, let's see if this fits. Actually, I'm just going to reduce the size. At this point, I don't even know how to write on paper anymore because I'm so used to this. Just really bad, actually. 8 2s are a 16. If you give me a paper, I wouldn't know how to do mathematics anymore. Okay, so therefore we have a 2. Oh, why is the n? It should be n naught. Oh, this is a bad mistake. Okay, 2 into, okay, n naught plus 8/15 into 4 power t minus this expression, and then we have a plus 9/10 minus a 16/15, and we can just take an LCM, make a common denominator, and this should become 9 multiplied by 15 is 135. My 10 multiplied by 160 is 160 over 150. So the final solution will be minus 25/150. As you can see, since the value of the roots is greater than a 1 in absolute terms, therefore if I take the limit of xt as t approaches infinity, this is just going to go to an infinity, right? So but if you ignore this, let's see this when there's no shock. Okay, so whenever time approaches a 0, or basically actually even that's not the steady state, because let me think about that, because we don't have the values over here. So I think the value of the steady state is just the particular solution, right? And the particular solution is always the constant that's being added. So x star should be a minus 25 over a 150. So this should be the steady state, which is unstable, the value of x. Okay. Similarly, let's find the value of y. Yt is equals to mt plus 3nt. Okay, so it's an mt plus 3nt. We have the value of mt, which was right here. Okay, and we have to, oh, let me just remove this. And we have to add and multiply the value of nt. This was the value of nt, where 8 3s are, I think it's 8 3s are 24. Yeah, I think so. I'm so bad at basic multiplications. Hilarious. Okay, so the final solution is this and this right here, and then we can take a common denominator, 9 into a 15 plus 24 into 10 over a 150. Okay, so then we'll get our particular solution, which is basically going to be 240 minus plus 135. Okay, so it's going to be a 5 over a 2. Okay, so the steady state is y star, which is the particular solution, which is a 5 over 2. So this is the homogeneous solution and this is the particular solution. This is the homogeneous solution and we've added the particular solution. Remember, the particular solution is always the long run. It's always the steady state. So x star and y star is a minus 1 over a 6 and a minus 5 over a 2, and this is an unstable steady state. Okay, at part B, check the stability of the model. I've already commented that the model is unstable, and explain in words how we trace the trajectory in the event of a shock such that 5 increases to a 10. So a 5 increases to a 10. As you can see, the fact that if 5 changes to a 10, it doesn't change the matrix D, it doesn't change the matrix P, it doesn't actually change anything besides the besides the particular solution, right? So we can see the matrix, the column vector G actually comes here, changes nothing is besides the value of the steady state. So if initially our column vector was a 5 and 3, and now it's become a 10 by 3, it basically means that the x star, right, is going to change. Even y star is not probably going to change. Yeah, it's not. So shock, what we can write is a shock from 5 to 10 changes only the intercept, right? Because it's the curve itself of xt, suppose, could just shift up or down depending on if we had a negative or a positive side. And actually we had a negative sign, so it's going to like shift down, right? So only the intercept is going to change, thus leading to the only the steady state changing. So only the steady state changes, right? And we should also comment that the eigenvalues are still unchanged, right? Because the matrix A and B and D are unchanged. So system is still unstable. So that's it for question 2. In the next video, I'll solve question 3 given that Professor Zahid gave in the final exam. He gave a total of 4 questions. So I'll make a video on all 4. So it helps the next batch that take admission in LUMS to do better in this course. Okay, I hope this was helpful and I'll see you in the next one. Take care.